Okay, so the last lecture, last lecture we have seen about your problems related to. So you have seen the problems. You have seen about the problems related to IDFT. So in that IDFT, we have seen two methods. Okay. So in this IDFT, we have seen two methods. One is the normal method. Okay. So the normal method that we will be using for finding the IDFT using the formula, and the second method is using the matrix method. So this matrix method is somewhat more easier to compute. Okay, it will be somewhat more easier to compute using your formula. Okay, in terms of the matrix. Okay, so the formula will be in terms of the matrix, and using the matrix you can easily find out the required formula. So in that you have to know about I'll be recalling only one formula, that is your matrix format. You have to know about the twiddle factor. So this is the formula you have to know. This twiddle factor I will be writing the formula. So the twiddle factor WNK, so WN of K, okay, WN of K, this will be equal to e power minus e power minus j, e power minus j 2 pi, e power minus j 2 pi K small n, the whole divided by capital N. Okay, so this is your formula for your twiddle factor. So based upon this twiddle factor only your matrix will be defined. Okay, so this is what we have seen in your last lecture. And in today's lecture, what you will be seeing is we will be dealing with your properties. Okay, so in today's lecture, we'll be seeing about the properties, and these properties, more or less, these properties more or less we have seen in your, what you can say, uh, we have seen in your DTFT. Okay, the same properties will be repeating over here. Okay, well, using the example, it will be more easier to understand. I will be just saying about the properties, and you just have just a glance about it, so it will be very clear to you. Okay, while doing the problems. These properties you already know. The same properties only it is repeating again. So we will be getting into the properties of DFT. So it is more or less similar to your same properties that we will be seeing in your DTFT. Okay, with some changes. Okay, so what they are saying is first property is about your, the first property is about your periodicity. So you know about periodicity, I have already said. That is, your signal will be repeating for a particular time period again and again. So that's what your what you can say periodicity implies. That is, if x of n, okay, if x of n plus n, okay, so this n corresponds to your periodicity. Okay, x of n plus n is equal to x of n, okay, for all n. Then if you are taking, okay, if it is periodic, this signal is periodic signal means your x of n plus n will be equal to x of n. Okay, at the same time, if x of k, that is after taking DFT, so this is before taking DFT and this is after DFT. After DFT, your x of k plus capital N will be equal to x of k. Okay, so this is for all k. So this is the initial condition for your periodicity. Okay, so then by the definition.
சார் கோகிலாவுக்கு அக்செப்ட் கொடு.
Okay, okay. Okay. So getting into the topic again. So this is the initial stage. So for as per your definition of DFT, okay, as per the definition of DFT, what happens is that your x of k plus n, okay, so this n is the periodicity, okay, so this will be equal to summation n small n equal to 0, okay, n minus 1 x of n, okay, x of n. So the change will be coming in a e power, okay, in the e power only the change will be coming minus j 2 pi n k plus n by capital N. Okay. So this is what your definition for your DFT. Okay, if you're taking the DFT means this is the definition. So now here what happens? You have to separate it. Okay. So separating means summation n equal to 0, n minus 1, okay, x of n. So you are separating this. So it will be e power minus j 2 pi. So you multiply this inside, so it will be k by n, okay, k by n into e power. So here there is n, so it will be minus j 2 pi capital N k by n. So here this n gets cancelled. So it will be sorry here this k won't be coming. This k won't be coming. Okay, so this n will be cancelling. So it will be e power minus j 2 pi into n. So here there's n. One n is there. So that is small n. Okay, small n. So this value will be taking the value as 1. That is e power minus j 2 pi will be taking, that is 2 pi is there. So here if you are applying your cos pi, that is the e power j formula means you will be getting this minus of minus 1, so it will be 1. Okay, so this value becomes summation n equal to 0 n minus 1 x of n. So it is the e power minus j 2 pi k, it is nk by capital N. So it is same as that of the, it is nothing but the same as that of the x of k. So this thing, this formula. So this is same as that of your x of k. So what you got is your x of k plus n is equal to x of k. So we have proved this. Okay. So we have proved this step. So getting clear? So so this is based upon the periodicity. So next we will be getting into so next is based upon the linearity. So linearity you already know the same thing. So second property is based upon your linearity. Okay. So I think you understand this. The first property. We'll be getting into the second property, linearity. Here, what they'll be doing is they'll be multiplying with a constant, similar to your linearity property in your DTFT. They will be multiplying with your constant, and if that is after that your signal will be multiplied in terms of the. Wait, I'll be explaining. So for this, you'll be taking two signals. Okay. So if you're taking the signal DFT means, so the first signal you can take as x1 of n, and the second signal you can take it as So x1 of n. So if you're taking DFT means it's x1 of k, and the second signal you can take it as DFT of x2 of n. You're taking means, so this will be your x2 of k. Okay, so this is the thing. Now what you will be doing is you will be multiplying, that is you will be adding both the signal and you will be multiplying with your uh, constant. So if multiplying with your constant means what you will be getting is your DFT. We are multiplying with a x1 of n plus b x1 of n, so x2 of n means, so the final thing what you will be getting is will be equal to a into x1 of k plus b into x2 of k. Okay. So I'll be just explaining the property alone, and for this proof you need means you can refer to your Anand book. Okay, in your Anand book it is very clearly given. So the explanation is very easy. You have to take the DFT for the two signals separately, and you have to add it, and the constant you have to take it out. Okay, so then you will be getting the linearity. So next week we'll be getting into the third property. So the third property is based upon odd and even sequence. Odd and even sequence. Okay. So this is your third property. So for this there's a trick is there. What does that means? For even sequence, for your even sequence, your DFT will be, DFT is real. Real means there won't be any kind of J term. Okay. At the same time, for odd sequence, your DFT is imaginary. Okay. It is imaginary. That is, it will be having the J term. So this is what you have to know. So for this, the evaluation can be done. How it can be done means, first you can take even sequence. So in this you can omit your real and the imaginary part. Okay. So for this you have to know, what you have to know is the e power formula. Okay. So the e power formula is nothing but it will be, so your e power formula is, you just get into the e power formula. So your e power, so if they are giving e power j, okay. So here e power j 2 pi n k by n. So for this can be written as, how this can be written means, it can be written as cos of 2 pi n, okay, k by n, okay, minus of j into sine 2 pi n k by n. So here what you have to know is that, so as per your DFT formula, here minus will be coming. So if that minus is coming means, if this minus is coming means, here it becomes plus. Okay. So I'll be putting the minus over here. Okay. I have put on the minus, so this becomes a plus value. So now what we have to take, if you are finding for your even sequence means, you have to take only the DFT real. So the real part over here is, it is this part. Okay, it is this part. So this part is your real part. Okay, and for the odd sequence, you have to make it as, imaginary. So this is your imaginary part. So this can be written like, how it can be written means. So moving on, for your even sequence, can be written as x of k equal to summation n equal to 0, small n, sorry, small n is equal to small n equal to 0, okay, 0 to here n minus 1, n minus 1, x of n cos 2 pi n k by n. Okay, so we are only taking the real part. We are omitting the imaginary part for your even sequence. Now for your odd sequence, so odd sequence, what you will be doing is x of k will be taking your imaginary part, so it will be sine. So summation n equal to 0, n minus 1, x of n sine 2 pi n k by capital N. Okay. So I hope now it will be clear for you. So for the important problems alone, I will be that is important properties alone, I will be covering with the proofs. Okay. So for this, the proof is no needed because you already know your e power term is nothing but you can expand like this. And for the even sequence, you will be taking the real part, and for the odd sequence, you will be taking your imaginary part. Okay. So like that it works. So now moving on to your fourth property. Okay. Fourth property will be seen. So this is with respect to your third property. And the fourth property is time time reversal. So this is what your fourth property is. So now, as per the time reversal property, what they will be saying is this is similar to that of the thing what we have seen with respect to DFT. That is, if it is a negative value means okay, uh, you will be just what you can say. So you just have a answer what the definition I'm giving, but if you're going into the problem means only you'll be getting understand. Okay. So this is defining the property. Okay. So x of n is your signal. Okay. So this x of n we're taking DFT means what it becomes will be your x of k. Okay, so this is what your normal DFT. So here what they are saying, as per your time reversal, if the DFT is taken for the x of n in an anti-clockwise direction. So as per we know, this will be your unit circle. Okay, this will be your unit circle, and in this unit circle, okay, in this unit circle, if you are taking the sampling at any random points, then it contributes to your DTFT. But if it is taken at equal points, then it contributes to your DFT. Okay. So here we are talking about DFT. So as I said, for taking DFT, we'll be calculating in your clockwise direction. Okay. In the time reversal property, what we'll be doing is we'll be taking it out in an anti-clockwise direction. Okay. So this is the main difference. So if you are taking the signal in the anti-clockwise direction means, so for your x for at this time period will be x of n. Okay, and over here it becomes x of minus n because generally we'll be moving with the clockwise if you are speaking with respect to DFT. But in the time reversal property, this x of n signal will be moving in terms of your anti-clockwise direction. Okay. So now what happens? So now we are taking the DFT for your anti-clockwise direction. Okay. So now what happens is, so while taking the anti-clockwise direction, you have to have one knowledge that this signal must not get into the negative. Okay. So you'll be taking the mod value for the sampling sequence n. Okay. So you'll be taking the mod value for the sampling n. So now what happens is that DFT of x of minus n comma mod of n. So this value will be equal to DFT x of n minus n. Okay. So now we are taking the DFT for this means it becomes x of, so the k value in normal thing it will be k. Over here it becomes x of minus k comma the mod of n. Okay. So this thing if I am representing with formula you can sorry problem you can just understand. So this becomes x of n minus k. So this is your time reversal property. So other properties are there. So you just refer your Anand book. So the next property is, okay, I will be just giving the proof for this. Then it will be easy for you to understand the other upcoming proof. Okay, so for the proof for this, okay, so in normal DFT of x of n minus n will be equal to summation n equal to 0 n minus 1, okay, x of n minus n. That is, so this signal is just replaced with this. So n e power minus j 2 pi k, okay, by n. So now, and here there will be another one n. Okay. So now what we'll be doing is we'll be changing the index. Okay. So as per your time reversal, we're just changing the direction. So what happened is that changing the index from n to m. Okay. So your m will be in general it will be n minus n. So here you have to replace your n. So your n will be equal to n minus of m. Okay. Now apply this value over here, over this here. Okay. So now what happens? DFT x of n minus n will be equal to summation. So the n is replaced. So m will be equal to 0. So this will be given by n minus 1. So x of m, okay, so it is replaced. So x of m e power minus j 2 pi k n minus m by capital N. Okay. So now we have to separate it. By separating your DFT of x of n minus n will be equal to v power, sorry, summation summation m equal to 0 n minus 1 x of m, okay, will be take separately taking the e powers, e power minus j 2 pi by n, 2 pi by n, here it will be k and here it will be n into, so here it is into e power minus, sorry, it is plus, so here there is already one minus is there, so it will be plus j 2 pi by n k into m. Okay. So now here what happens? This n and n get cancelled out. So there will be e power minus j 2 pi. So k is a constant. So this value becomes, this value becomes, what it becomes? It becomes 1. Yes, this value will be taking the value of 1. So now what happens? It will be e power minus, that is m equal to 0, n minus 1, x of n, b e power minus, that is plus, right? So j 2 pi by n k into m. So now, for simplicity and for the sake of getting out the result, what we'll be doing is we'll be multiplying this with another one term, summation m equal to 0, n minus 1, x of n, okay, x of n, e power minus, that's j, this j will be there, so 2 pi by n, k, this will be there, into, for our simplicity will be writing, okay, to get the answer, e power minus j 2 pi, yeah, so this value is also will be 1, okay, this value is also takes the value of 1, okay, so now we can combine this and this to get the needed answer. So now what happens? So now this becomes summation m equal to 0, n minus 1, x of m e power minus j 2 pi m n minus k by m. Okay. So now this becomes the DFT of x of n minus m, so n minus n we can have n minus n, this will be equal to this answer, which is nothing but your x of n minus k. So this is the answer we need and we have got. So this is the proof. Okay, this is the proof for this property. Okay, next there's another one small property. I'll just okay. So other property you just refer the on of the book. There are another more 3 to 4 properties. So now we will be getting into the problem. So after this, there's another one important theorem. While getting into the theorem, I will be explaining about that. Okay. So I think it's not visible for you. So next we'll be getting to the problems. Okay. Yeah. Okay. So the properties you just see in your Anand Kumar book, and now we'll be moving towards the problem. Okay. So, so I think it is. I don't know about the problem number. Okay. It is around 15, I think. 16, I think. You can take example 16. Okay. So here you can see. So given further given x of k as a 12 point DFT. The 12-point DFT means it has 12 samples. 12 samples. So your n value will be taking as 12. Your n equal to 12. Okay. So 12-point DFT of a length. So length they are given us the, so this length corresponds to the number of sequence of length 12 real sequence. Okay. So this corresponds to your number of samples. The 12-point DFT means nothing but, so you have to know about the point DFT. Okay, so this is what corresponds to your sample length. So 12-point DFT refers to nothing but your unit circle you will be taking, and we have already seen the 4-point DFT. 4-point DFT in the unit circle you will be equally taking into the 4 points. Then it is 4-point. At the same time, if you are taking equally into the 8-point means, so it corresponds to the 8 points. So now for the 12-point, it will be taken in terms of the 12 points. Okay, the circle will be equally divided into or sampled into 12 points. Okay, so they have given this. So this is the meaning for your 12-point DFT. So in this first 7 samples, it is also given only. So given is not finished. First 7 samples of x of k, okay, given us. So they are giving the first 7 samples. So in your x of 12 point 12 DFT, your x will be varying from 0 to x of 12. Sorry, not 12. So 0 is there, so it will be varying up to x of 11. So now in this they have given up to 7 samples are given. First 7 samples are given. So what are those means? First x of 0. So it is given only x of 0 is 8. X of 1, it is equal to -1 plus j into 2. Okay, x of 2 will be equal to 2 plus j into 3. Okay, x of 3 will be equal to 1 minus j into 4. Okay, x of 4 is given as -2 plus j into 2. Okay, and your x of 5 is given as 3 plus j, that is 1j. Okay, and x of 6 is given as -1 minus j into 3. Okay, so these are the 7 samples they are given out of 12. Okay, so to find what they are asking to find the remaining samples, the remaining samples. So here, what you have to do is this is similar to that of your shifting. Okay, uh, that is in the last class while we are seeing about your 8-point DFT. Okay, what it happened was after sorry in the 4-point DFT. What it happened was after some periodic time the values got repeated. Okay, so if they're asking problems like this means so in the 12-point DFT also after the 6th value so that's the concept. So your signals will be repeated again. Okay. So now what happens? You have to find the repeated signal. Okay. So solution to find the repeated signal, what you can do is that so your n value is first you take the n value, n is 12. Okay. So over here you already know as per the shifting property, x of k will be equal to x of okay, x star n minus k. Here the star represents nothing but your conjugate. Okay, you have to take the conjugate. So I'm explaining with this example. So now you apply your n value. So it will be x star 12 minus k. So now what you need is the samples. Okay. So for your x of 7, so your x of 7, you have to put x star of 12 minus 7. So it will be x star of 5. So your x of 5 is nothing but 3 plus 3 plus j. For this you have to take the conjugate. If you are taking conjugate means nothing but the uh, j term will be become negative. So it will be 3 minus j. Then x of 7 value is this one. Okay, 3 minus j. Now for your x of 8. X of 8. X of 8 will be the same formula. X star 12 minus 8. Okay, it is x star 4. It will become minus 2 minus j into 2. Okay, so your x of 9, same thing, x star 12 minus 9, this is nothing but your x star of 3. It will be equal to 1 plus j into 4. So next x of 10, so this will be equal to x star of 12 minus 10. It will be x star of 2. It will be equal to 2 minus j into 3. Okay. So x of 11 equal to x star of 12 minus 11. It will be equal to x star of 1. So it will be as taken as minus 1 minus j into 2. Okay. So this is how you have to solve the problem. Okay. When we close the session with a small property, I take it as a property. So property 6. So what's the property is nothing but a complex conjugate property. Okay. So as per this property, what they're saying is, so often is your signal. So if you're taking DFT for this, what happens? It becomes x of k. Okay. Then, as per this property, if you're taking the conjugate, this means, okay, if you're taking the conjugate of the signal, DFT for the conjugate of the signal means DFT of x star of n. You're taking means, so what happens is that this becomes, you have to take the conjugate. So based upon this only, we have all the previous problem. Okay, n minus k. So this is what your property. Okay. How this happens? You can see. So the proof. Okay. For the proof, DFT x star of n be equal to normal thing. Okay. Instead, that be x star only different. Okay. So this becomes n equal to 0, n minus 1, x star of n e power minus j 2 pi k n by n. Okay, so here this alone becomes the conjugate. So that's the only difference. So next, what it happens? So the DFT of x star of n okay, this will be equal to you have to take the conjugate. Taking the conjugate means will be summation n equal to 1 n minus 1 okay x of n e power the conjugate you are taking as a whole out. So this minus j becomes a plus j component. So it will be 2 pi n k by n. Okay, this the whole conjugate. Okay? This the whole conjugate. Okay. Now what you have to do? You have to substitute the value of n. Okay, so substituting the value of n means it becomes n minus k. Summation n equal to 1. Sorry, n equal to 0. 0, 0, n minus 1, x of n, e power minus j into 2 pi n into n minus k by n. Okay, this is the whole conjugate. So either what you can do is that you can just find this value and you can substitute to RHS. Okay, and then you can put this as x star of n minus k. Okay, and then you can find the DFT for n minus k, and you can take an LHS and you can just equate it and say both are the same. Okay, so this is what here another property. So this property also they have given clearly in your component book. Okay, so you just refer with that, and we'll be closing today's session with this. Okay, we'll be closing it.